In this video, we are going to discuss Chapter 2, Simple Comparative Experiments. So, there are two parts to this chapter. In first part, we are going to review some basic statistical concepts. These concepts you have already studied in your statistics class, but we are going to have a quick review so that that will be our foundation on which we will build the complex statistical models in this class. So uh, those basic statistical concepts, they include things like random samples, then population versus sample, right? Sample mean, variance, and standard deviation. Population versus population mean, population variance, and standard deviation. Is how to estimate parameters, right? How to estimate population parameters from sample parameters. And so that's the first part, to have a good understanding of these things. And then in the second part, we will discuss the various types of simple comparative experiments. So, where we have to understand the hypothesis testing framework, we will study the two sample t test, then how to check assumptions, our assumptions in our statistical model, how to validate those assumptions. So I'm going to divide this chapter into multiple videos. So this video will mostly focus on these basic concepts, and then we will study something called as z test. So without further ado, let's get started. So I have a problem statement here. Maybe I can open a book for you and I will read the problem from there. Okay, let's see. So let's go to chapter 2. So here is the problem statement that we are going to work on in order to understand uh, the basic statistical concepts. An engineer is studying the, maybe I will increase it a little bit so we can read it. An engineer is studying the formulation of a Portland cement mortar. He has added a polymer latex emulsion during mixing to determine if this impacts the curing time and tension bond strength of the mortar. The experimenter prepared 10 samples of the original formulation and 10 samples of the modified formulation. We will refer to the two different formulations as two treatments or as two levels of the factor formulations. When the cure process was completed, the experimenter did find a very large reduction in the cure time for the modified moisture formulation. Then he began to address the tension bond strength of the moisture. If the new moisture formulation has an adverse effect on bond strength, this could impact its usefulness. So basically, as you can see, the engineer is trying to compare the two different cement mortar formulations, right? One is the unmodified original, and another one is modified, that he has modified. The idea here is to reduce the curing time by modifying the original formulation. He's trying to reduce the curing time, and it says that uh, he did find that very large reduction in curing time for his modified formulation. So that was good, right? That was good that he was trying to achieve, but at the same time, uh, he wants to make sure that the tension bond strength of the cement formulation is not changed, right? In order to reduce the curing time, he doesn't want to compromise the tension bond strength of the modified moisture. So he needs to compare tension bond strength of the original formulation to the tension bond strength of modified formulation. And here we have these. So he conducted some experiments. Again, there must be some information about that. 10 samples, right? 10 samples of modified formulations versus 10 samples of original formulation. So here we have the data here. We can see that the tension bond strength data for the Portland cement formulation experiment. So we have modified moisture, 10 samples, and we have their tension bond strengths listed here, and unmodified moisture, tension bond strengths listed there. So looking at these two data sets, what it's very difficult to say whether there is a decrease in tension bond strength of modified moisture versus the unmodified moisture, because the numbers are kind of all over the place. So maybe you can, if you like, for example, if you see here 16.85 in the first sample, 16.85 versus a sample you compare from unmodified moisture, 16.62. So here you will see that the tension bond strength actually improved, versus you look at the observation number 10, 16.57 and 17.27. So tension bond strength has decreased. So uh, hard to compare because numbers are as kind of all over the place. So we need to plot this data. Uh, we need to look at it visually, right? Once we plot the data on a graph, then that will give us better insights as compared to just looking at this raw data. So here the dot diagram for tension bond strength is plotted. So you can see unmodified formulation, uh, the dots here that represents the 10 samples, and we have this on x-axis, we have their tension bond strength values, and unmodified the first row and modified the second row. So one thing you will notice here, if you closely examine the data, that there is a shift. Unmodified has a shift towards the right as compared to the modified formulation. That means that shift means here we can at least see that unmodified formulation has, from based on this shift that we are seeing in the data, has higher tension bond strength as compared to the modified formulation. Also, one other thing you can do is maybe you can take the sample average. You can take the average of these 10 tension bond strength values for unmodified, and same you do for modified, and then you can compare these two averages, and that will give you some idea. So this is a dot diagram that we generally draw to visually look at the data. Then, so that's one, right? So in so this is a sample, not population, right? We're not talking about uh, all formulations, entire population of formulations that engineer can come up with. No, uh, he took a small sample of 10, and that's why we are just the data is basically a sample data, not the population data. And so this, and then next thing we talked about is looking at the data graphically or visually, because just raw data, it is hard to say, hard to come to any conclusions just looking at the raw data, right? Particularly when the numbers are very close to each other. So that's why we try to plot the data here. The dot plot is a dot diagram, is a very popular chart to look at the data visually. Another visual aid is histograms. You may have seen histograms before. Now here, the histogram that is shown here is not for the same data that we are talking about. This is a histogram for 200 observations on metal recovery yield from a smelting process. Right Now, the histograms are most useful when we have a large sample of data. Like in this case, right? We have 200 observations, and you'll see on x-axis we have the yield values, and y-axis we have frequency, or this is another scale, relative frequency. And then you, from histogram, you can things like you can look at things like the central tendency of the data, and the spread of the data, right? Things like that. We can our sample is small, so histogram may not be that useful for our problem. Now, the another chart that we can plot is box plot, and here is the box plot for our problem: modified versus unmodified. So in a box plot, you will see again there is a shift. On y-axis we have strength. The unit of the strength is kilogram force per square centimeter, and you will see that there is a upward shift in unmodified moisture, the original formulation, as compared to the modified formulation. That means by modifying the original formulation, we are seeing the downward shift. We are seeing the strength is decreased, right? Strength is decreased. Now, it's it's not obvious because there is the box. This box plot is not like way up here and this is way down there. There is no like there is some crossover, right? uh, so they are not completely separated from each other. So one question can be, is this a statistically significant difference, or is this just a noise? If we take another 10 sample, do we see modified up and unmodified down? How can we know that this is the true statistically significant difference and not just noise? Right. That's why we are going to need some statistical test to confirm that, particularly because there is some crossover between the two box plots. So it is not quite obvious as such, but it is my hunch, and you can also see that there is something. The shift seems like a real shift, not just noise. But we'll find out, right? But this is another plot that we can plot. Now, can we plot these ourselves? Yes, we can plot these charts in Excel. So let's do that. I have here Excel file here. So, and I have already have the data documented in this Excel file. So first thing I want to do is make a dot plot, right? But to make a dot plot, uh, we need to basically organize data in a different fashion. So I will open a sheet 2 here, and what we'll do is we'll copy these observations, and I will copy them here. And so maybe I will have a header row insert. So here is the type, modified versus unmodified. Here we have tension, bond, strength. Okay, this is basically the, or we can say, formulation. And I would like to use, for modified, I would like to use number one for modified, and for unmodified, I would like to use number two. Just some designators, right? So these are all belongs to these observations all belong to modified formulation. So that means formulation one, right? Because we are okay. Because Excel need, to create a proper dot plot, Excel will need this in number format than just writing modified versus unmodified. So then I will copy these values here for unmodified formulation. Okay, and the, the designator is 2, unmodified is 2, right? So okay, so we got that. Okay, so next what we need to do is create that dot plot. So I'm gonna go to insert. Maybe I will select the data here already before I select insert chart, um, and we can do the scatter plot. That will now you will see here, uh, and we can, if you want to change the scale is 1 or 0 and 2, and we want difference is 1. It's really the they are not numbers. What I want to say is 1 is for modified and 2 is for unmodified, and these values here, the tension bond strength values. And as you can see, there is a shift, right? There is a shift for unmodified. uh, the graph in the presentation that we have is horizontal, and this graph is vertical. So if I show you here, it's the same graph, but here the graph is horizontal, unmodified and modified, and our graph here is vertical. So that's the dot plot. Now let's me show you how to make the box and whisker plot, or box plot generally it is called. So for that, if I select these two columns on the sheet one, here we don't need the data to be organized in this other fashion. So we select the data, insert chart. It's not a scatter plot, so I need to go select all charts and see box and whisker, right? Here we go. So the orange is unmodified and the blue one is modified. You can add the chart title and other things, but once again, the whole point of making this chart was to show that there is a shift uh, between modified and unmodified. Now, whether that shift is statistically significant or it is just a noise, that we will find out by performing some tests. But at least visually, it's looking at the data visually is much better than just looking at the raw data. Here we can clearly see the shift that was not possible to see in the raw data. So let's get back to the presentation here. So now we know how to make dot plot and scatter plot. Next thing is to understand the hypothesis testing framework. And you should be familiar with this because you all have taken at least one statistics class. So it's a very, as you know, statistical hypothesis testing is a very useful framework for many experimental situations. It originated in early 1900s. We will use a procedure uh, for this comparison between two groups, right? The name of the chapter, it said, is simple comparative experiments. We are comparing two groups. And our statistical hypothesis will be in the context of that. Uh, and to uh, statistically prove whether to accept null hypothesis or alternative hypothesis, we will use two sample t test. So how does that work? So in statistical hypothesis, we have two hypotheses, right? The null hypothesis is mu1 is equal to mu2. What is mu? Mu is the population mean. So, for example, if we say one is unmodified, or one is modified and two is unmodified, right? So the if you take the mean of all the population of modified and mean of population of unmodified, mean of what? Mean tension bond strength. So those tension bond strength mean they are equal. That means there are no differences, right? And versus the alternative hypothesis, mu1 is not equal to mu2, means there are differences between the two populations tension bond strength. And of course, we, as I said, it is we cannot know what mu1 and mu2 is. All we can have is the we can collect a small sample. In this case, we collected a sample of 10, and then we calculate sample average, and that sample average, which is, we can call it uh, y bar, right? So for example, sample 1, this is a very generic framework, but I'm discussing this in the context of our problem. So two groups, right? In this case, modified versus unmodified. In other problems, it would be something else, but two different groups that we need to compare. And the sample that we collect, sample points y11, y12, y1 and 1. So this is, in our case, we got 10 samples, right? Similarly, for the second group, in like modified versus unmodified group, again we have 10 samples. These samples are hopefully coming from a normal distribution with some mean and mu1 and variance sigma 1 square. So normal, as you can see, these are bell curves, normal curves, right? So the data generated, sample data for, in our case, tension bond strength generated for two different groups, there is normally distributed. The sampling from a normal distribution. Okay. Then y bar, as I said, we have the tension bond strength of uh, the each of the 10 samples. We can add them and divide it by the number of samples. That will give us the sample average y bar, and that will be the estimation of population mean mu. And sample variance, because we also don't know the population variance sigma square, right? So we can calculate sample variance, which is basically given by this formula: summation of yi, individual values, minus y bar, which is the sample mean, whole square. We sum it from I is equal to 1 to n, and divided by n minus 1. So that's a sample variance, and that is the estimation of the population variance, because we don't know the true population variance. So here is the summary statistics for the two groups that we have: modified moisture versus unmodified moistures. So we can do that in Excel. uh, so let's try to uh, find that. I'm just going to move this chart so we can uh, have some space to write down those the descriptive statistics of this data, right? So you can literally manually calculate here, right? You can add this number. So suppose you want to calculate the sample average, you can add this, divide by the number of samples, and so on and so forth. But I'm going to use I'm going to the specific tool that we have that will give us all kinds of descriptive statistics. So I'm going to go to data data tab in Excel, and data analysis. Okay, here we have if we scroll up, we have a descriptive statistics is what I'm interested in, right? Descriptive statistics. uh, okay, and input range. So I'm going to select these two columns as my input range. These are grouped by columns. Yes, they are grouped by columns. One column is for modified, another column is for unmodified. Are there labels in the first row? Since I selected row 1 also, yes, there are labels in the first row of the data that I selected, right? Now, where do you want to put your output range, your results? So that, let's put the results starting somewhere here, okay? So we are going to put the descriptive statistic results starting from cell D1. And what do you want to put? What results you want to output? There are different things you can do, but I just want summary statistics, right? Like mean, standard deviation, variance, and things like that. So I'm gonna click OK, and here is our data. Mode Mode means the number that is in each set, the number that repeats the most number of times is mode, but there is it says not applicable, not applicable because there is no number that is repeating. So that's why there is no mode to this both data sets, right? So uh, this first so this here is for modified. Let me make it thick border out and that, and this is for unmodified, the second two columns. So if you look at, we are not interested in all of the information here, but it's good to have everything available to us there, right? So mean y1 bar and y2 bar, 16.764, and that we have standard deviation, we have median, we have uh, variance, right? Standard deviation is here actually, standard deviation. Then we have sample variance, and this, if you look at this, uh, this should match with the data we have. Like for example, variance is zero point 0.1 for modified and 0.061 for unmodified. So you can see variance is zero point 0.1 for modified and 0.061 unmodified. So what we learned is how to generate uh, descriptive summary statistics in Excel using the data analysis tab, right? So we have that. Sample averages, sample variances, sample standard deviations, and the sample size n1 is equal to 10 samples, n2 is equal to 10. So with that, now it's time to perform the t-test. We really want to find out whether there are differences in the tension bond strength of two formulations. So first thing obviously we can do is we can take the difference between the sample averages, right? Y1 bar minus y2 bar, and that is point minus 0.28. So there is this difference that we found in these two samples, correct? But is that statistically significant? Like if we collect another two samples, are we going to see that difference consistently, right? So uh, the the t-test that we are going to use to verify if this is statistically significant or not is basically works like this: the difference in sample means divided by standard deviation of the difference in sample means. So as we know that the variance of y bar is equal to variance divided by n, which is sample size. So variance of the sample average is calculated by uh, the variance of the data divided by sample data divided by the sample size. But we want the and the standard deviation is square root of variance, right? And we want to find out. We already know the difference in sample means, which is minus 0.28, but we want to find out the standard deviation of the difference in sample means. So first we can calculate variance and then we can take a square root of that. So from this formula here, variance of the difference in sample means y1 bar minus y2 bar is equal to, from the right hand side here we can use that, sigma 1 square divided by n1 first sample, uh, plus sigma 2 square divided by n2. And the assumption here is y1 bar and y2 bar are independent. That means there is no correlation between these two samples. They are independent of each other. So this suggests statistics, z statistics. Going to talk about t, but bear with me. Right now we are this is the z statistics that is shown here. Z statistics, basically what is that, is represent a standard normal distribution. So z0 is equal to y1 bar minus y2 bar, difference in sample means, divided by, because we want to divide by standard deviation and we have the variance, we need to take the square root of variance, right? Square root of variance. So that gives us this z0 value. If the variances were known, we could use the normal distribution as the basis of a test. And this we can use z test, right? Z0 has a normal distribution with a mean 0 and standard deviation 1. So we know that any normal distribution with mean of 0 and standard deviation of 1 is called a standard normal distribution, right? So z0 has a standard normal distribution if the two population means are equal. If they are equal, then we will get z0 as a standard normal distribution. But if population means are not equal, then they will not have the standard normal distribution. So that we can use as the basis of test, provided that we know the population variances, right? Uh, Again, let's not confuse between the population variance and sample variance. What we have here is a sample variance, right? So we really don't know and sample variance is an estimate of the population variance. But uh, so the question, if the variances were known, but we don't know the population variances, right? So let's continue on the next slide. If we knew the two variances, how would we use z0 statistics to test the null hypothesis? Suppose we know the variances or we know the standard deviations, right? Let's suppose that both populations, the modified and unmodified, I'm not talking about sample, I'm talking about the entire populations, right? Sigma 1 is equal to sigma 2 is equal to 0.3. So uh, standard normal, the standard deviation is provided. So we know the standard deviation, right? Then we can calculate the z0 value, y1 bar minus y2 bar divided by sigma 1 square by n1 plus sigma 2 square by n2. So 0. This difference is minus 0.28, we know that. Sigma 1 square is 0.3 square, sigma 2 square is also 0.3 square, divided by the sample sizes, respective sample sizes 10. So that's going to give us value z0 minus 2.09. Now, how the question is, so what do we do with this? Once again, our main goal is to determine whether there are differences in tension bond strength of the two different formulations. So for that we perform this we are performing this z test, and just now we calculated the z0 value, right? So the next question is, how unusual is the value of z0 minus 2.09 that we got if the two population means are equal, right? So to find that, we need to look at the z tables. So it turns out that 95% of the area under the standard normal curve falls between uh, one g of 0.025. Now you will say, what is where this 0.025 came from? So we generally use the 95% confidence interval, right? Or a significant, another way to say that is, we use a significance level of 5%, or alpha is 0.05. Alpha is a significance level 0.05. And since the z distribution is like you look at this, it's a two tail distribution. There's a tail here and tail here. So that 5%, 5% in this, so this is 95% is here, right? If we use that, and the 5% area is remaining in the tail. So half of that 5% is in this tail, half of 5% in the left tail. So half of 0.05 is 0.025, and same 0.025. That's why we are talking about 0.025. So what is the value of z at that 0.025 that we want to find from the standard normal distribution tables? And once we find that, you will see if our calculated z value, which is minus 2.09, right? If that is beyond the z value, that is like beyond that 0.025 value there, right? Beyond, same thing on the right hand side, it's or here, beyond that z value at alpha significance level 0.05, then we should say that that is highly uh, not possible. That means we should reject the null hypothesis. That means that those means cannot be same. So let's see where how did they got 1.96. So if we go back to the book, in our book we have at the back of our book we have the standard normal distribution tables in the appendix. So I'm going to uh, go to the appendix here. Let's see, it's all the way to the end of the book. Okay, so here we have a cumulative standard normal distribution tables, right? And we are looking at the 0.025 value. So where should we look that value? These are the value we are looking for 0.025. So if you then standard normal distribution tables continue on the second page here. So here you will see that at uh, once again 1.96, right? So I'm trying to look for 1.96 here, 1.9 and 6. So here this is value we get 0.975. So if you subtract that, because uh, the what value is given, right? Or what basically the table is giving us the area under the curve, area under this curve, right? So what area is given? So area phi of z in this table, the area is given is from minus infinity to z. That means if z is here, minus infinity means from all the area before that z, right? And we know that beyond this tail it's 0.025, right? 0.025. That means we are looking for, if you subtract 0.025 from 1, you are going to get that 0.975. So that is that 1.96, 0.975. Or if you subtract 0.975 from 1, you will see the remaining tail is 0.025. So the tail, the value of g at that tail edge, right, is 1.96. 1.96. That's how we got these values here. 1.96. So our z value, calculated z value minus 2.09, and since this is a two-sided z test, on the right hand side we can say 1.96, on the left hand side minus 1.96, and our z value minus 2.09 is pretty unusual. If you compare that to with minus 1.96, it is way into the tail, beyond that value of minus 1.96. Pretty unusual. In what? In that it would happen less than 5% of the time, right? If the population means were equal. So we can conclude based on that, we can say that the differences in the tension bond strength of modified versus unmodified formulation, they are statistically significant. We should reject the null hypothesis that the means of those two formulations are equal. No, they are not equal. They are different, right? So we accept the alternative hypothesis. So same thing that I was trying to show you in the book is basically shown here, 0.975 value. And here is the summary that I just said. So if the variances were known, we would conclude that we should reject the null hypothesis at the 5% level of significance. So we should reject the null hypothesis of mu1 is equal to mu2 and conclude that alternative hypothesis mu1 is not equal to mu2 is true. This is, in another way, this is called a fixed significance level test because we are comparing the values of test statistics, the z0 value that we calculated with a critical value of z, which is 1.96, right? At, and we are using that 5% fixed level of significance. That's why it is called fixed significance level test. And the distribution that we used, the standard normal distribution, is our reference distribution for this test, right? Now, there is another way we can look at this problem. Instead of comparing with the fixed 5% significance level, we can ask what is the p value for our observed z value of minus 2.0, whatever that, minus 2.09, right? So basically, so let's say our minus 2.09 is, let's say here is minus 2.09, right? So we are saying instead of comparing that with that z value of 1.96, we are saying what is the this area here beyond minus 2.09, what is the area in the tail, and same thing on the positive side. If we can just calculate that area, okay, and if it is less than 5%, we should have the same conclusion, right? So uh, instead of using the comparing the z value with the critical value of z, we can actually calculate the area beyond that minus 2.09 z value, the area in the tail beyond that z value, and that will be our p value, and that uh, how small it is based on that, and we can compare that with significance, like 5% is generally anything less than 5% p value is, we are basically rejecting the null hypothesis because that is highly unlikely. So let's find out the p value from our table for our z value, right? So how can we do that? Once again, if you look at this here, it's easy to show me from here now that instead of going to the tables that, so let's take a look. Find the probability above z0 of minus 2.09. In our tables given in the book, they are only on the positive term, not for negative values, they are on for positive values, so we need to look for 2.09. They are same for negative, right? This is like equally distributed on both directions. So I'm looking at z value of 2.09. So z value of 2 here and 09, 2.09. And there I got that 0.98169. Okay. But that is the area to the left of that z value, all the area, minus infinity to z. We need to, but we need to find the area in the tail. So we need to subtract that from 1. And when you subtract that from 1, we get 0.01832. But that's just a one tail, right? We need an area in both the tails. So we multiply that by 2. So the p value is twice of this probability, which is 0.03662. So we can reject the null hypothesis because that value is way less than 5%, way less than 0.05. Typically 0.05 is used as the cutoff, right? So that is another way to look at the problem. So now, as you can see, this problem is very involved. First, you have to uh, calculate the z0 value for your data set, that for the two groups for which you have the data set. Then you have to take that z0 value to the standard normal distribution tables at the back of the book. You have to find what is the p value for the z value that you calculated, right? Then subtract that from 1, and that gives you area in one tail. Multiply that by 2, that gives you area in the two tails. And then compare that with the typical value of zero point zero 0.05. If it is less than zero point zero 0.05, you reject the null hypothesis. That means there are differences in the two formulations. If it is not less than zero point zero 0.05, you cannot reject the null hypothesis. That means what differences you are seeing is just a noise. The means are basically, there are no statistically significant differences between the two formulations. So much work. But can we do it easily in Excel? Yes, we can. They actually, Excel makes it much easier. So let's uh, do this problem in Excel. So let's see. So we have the two data sets, right? I'm gonna go to the data tab, data analysis, and we need to look at, let's see, z test two sample for means. This is the only option we have for z test, right? So z test two sample for means. Okay, and the variable one range is this. Variable two range is this. Hypothesized mean difference. When we say mu1 is equal to mu2 is our null hypothesis. That means our hypothesized mean difference mu1 minus mu2 is equal to 0. Even if we don't put 0 there, Excel is going to automatically consider that by default as 0. Now variance is the, if you go back to the presentation here, and you will see that, let's see, it's actually given to you. um, Suppose the standard deviation of group 1 and group 2 is 0.3, and variance is the square of standard deviation, so that is 0.09, right? So so that's where I have this thing here. Variable 1, which is modified formulation, variance is known variance, right? It's given to us 0.09. Variable 2, same, standard deviation is 0.3, variance is 0.09. Then this box here, uh, do we have labels in the first row? If you selected the first row, like we selected the data from A1, yes, we do have the labels, right? What alpha value we want to use? As we know, the typical alpha value is at zero point zero 0.05 that we use. So that's good. And now where do you want to put your outputs? So I'm going to place my output somewhere here. Okay. And just do OK there. So let's take a look at our results now. So first thing is, we have, of course, the means. The means are given. We already know that. Known variance is 0.09. There are 10 sample size, right? Hypothesized mean difference mu1 minus mu2 is equal to 0. And here is the z value that uh, Excel has calculated, minus 2.07. It's not going to be exactly precisely same, because the way Excel is calculating may be slightly different than the tables, or the tables may be, sometimes there is a rounding of things. Uh, but we got minus 2.07, which is very pretty close to minus 2.09, right? So that's looking good. And then the p value for that z value is 0.038. And as you know, this is less than zero point zero 0.05, right? Less than zero point zero 0.05. That means the null hypothesis should be rejected. There are significant differences between the two formulations. Or you can compare that. And we are looking at why I'm talking about two tail, because we are performing a two tail test, not one tail. Two tail means our null hypothesis is mu1 is equal to mu2, and our alternative hypothesis is mu1 is not equal to mu2. We are not saying mu1 is greater than mu2 or mu1 is less than mu2. If we say that, if we use that language, then basically we are performing only one side, one tail test. But since we are saying mu1 is not equal to mu2, we are performing two-sided test. So those Excel has given us both results. So I will basically hide this one tail test. So this is our calculated z value. This is the p value for that z value, which we need to compare with alpha value of zero point zero 0.05. Or you can compare that z value with z critical. If it is big, this is 1.95 on the right and minus 1.95 on the left tail. So minus 2 versus minus 1.95, this z value is greater than the z critical value. So any approach you use, let's keep this simple. Let's only look at p value and compare it with alpha value of 0.05. And if it is less, reject the null hypothesis. That means there are statistically significant differences. So that's how you perform a z-test in Excel. Now I will, this video is already getting longer, so I will stop this video here. And uh, the t-test we'll discuss in the next video. Thank you.